We talked about polarity and electronegativity a little bit. In a diatomic molecule, there's only one bond. And if that one bond is polar, then the whole molecule is polar. So here we have hydrogen and a chlorine, and we said the chlorine was more attractive. It's more electronegative. It's more attractive to the hydrogens. I'm sorry, to the electrons. And so we can indicate the dipole moment as an arrow pointing to the more electronegative atom. Here is electron density representation, where we have more electron density around the chlorine and less around the hydrogen, partial negative, partial positive charge. But when we look at polyatomic molecules, it depends on the geometry of the molecule. Because these dipole moments are essentially vectors. Vectors have magnitude and they have direction. And so if the dipole moments of the individual bonds cancel each other out, the molecule can be nonpolar even if the bonds within the molecule are polar. Let's look at carbon dioxide. Carbon dioxide has two carbon-oxygen double bonds. These bonds are polar. Oxygen is more electronegative than carbon. And so this oxygen pulls the electron density this way. That oxygen pulls the electron density that way. And we see these two opposing dipole moments. It's a little bit like carbon is in the middle and the oxygens are holding onto his arms and they're pulling in opposite directions. They're playing tug of war with carbon. And in tug of war, you want the flag in the middle of the rope to move, right? And whoever gets the flag across some line first wins. Well, if oxygen and oxygen are equally strong and they're pulling in opposite directions, is this going to move? No, it's just going to stay there. And they're going to pull on pull on carbon and his arms are going to hurt. If we think about vectors, we have a dipole moment that is a vector pointing this way and a dipole moment with an equal magnitude pointing in the opposite direction. And those are going to add up to 0. The magnitude is proportional to the electronegativity difference between the bonding atoms. So because this is carbon and oxygen versus carbon and oxygen, the magnitude of the vectors is the same. And if we look at the electron distribution, we see that it's symmetrical. Carbon dioxide does not have a negative end and a positive end of the molecule. It's symmetrical. Any questions? This is where things start to get a little strange. What about water? Water also has two polar bonds. But water's not linear. We just looked at why water is bent. So here we have an oxygen-hydrogen bond and an oxygen-hydrogen bond. The magnitude of those dipole moments is the same. But the directions are not directly opposing each other. We have one pointing in this way, in this direction, and another pointing that way. When we add those two vectors together, we end up with a vector going this way. We're going to look a little more detail about adding vectors. You can also think of tug of war, and here the oxygen is pulling, the hydrogens are pulling off to the side, and so the net movement of this group of 3 people is going to be in this direction, because oxygen is going to drag these guys. If they really wanted to oppose him, they should be on opposite sides, pulling opposite, and then nothing would move. But because water is a bent molecule, it does have a net dipole moment. So to identify the polarity, you need to, we got to have the Lewis structure so that we can get the molecular geometry. And then look to see, does it have polar bonds? If all the bonds are nonpolar, then the molecule is going to be nonpolar. But identify the polar bonds and make vectors that point towards arrows, that point toward the more electronegative atom, and make the length of the arrow proportional to the electronegativity difference. Determine if those polar bonds add together to form a net dipole moment. If they add to 0, the molecule's nonpolar. If there's a net vector, the molecule is polar. Does that sound like a lot of work? Yeah, it does. That sounds hard. Well, let's talk real quick about vector addition. In one dimension, it's easy. The vectors lie on the same line. One dimension is a line. And so we have one being positive, one direction is positive. So think of, back to elementary school and number lines, right? So here's our number line, and there's 0 in the middle, and this is +1 and +2, and this is -1 and -2. Right? And so going to the right is positive, going to the left is negative. Well, if we have two vectors that are both positive, they add up to 10. If we have a -5 and a +10, they add up to +5. This is basically just addition, right? If we have a -5 and a +5, they add up to 0. Vectors of the same magnitude in opposite directions. Everybody okay with one-dimensional vector addition? To do 2 or more dimensions, you have to start drawing some parallelograms. So if we're going to add this vector A and this vector B, we're going to draw a parallelogram in which the two vectors form two adjacent sides. So these are two sides of the parallelogram. So I'm going to draw this line up here. Let's maybe do that. Green, I don't know, green. So I'm going to draw this one. It's parallel with B. And then I'm going to draw one that's parallel with A and the same length. And adding them together is connecting the corners. So this red one is the addition of A and B. In this example here, I'm adding this vector and that vector. This one is longer, and we see from the sum of them that it pulls the sum over to this side. For A, I draw this line parallel to it, and for B, I draw that line. And then from where I started to where those two intersect is the sum. Now, in theory, most of you studied vector addition at some point. Some of you maybe repressed it. You've erased that part of your memory. What about in 3 dimensions, or three vectors, or more vectors? How do you do that? Well, you add 2 of them together first, and then you add that sum to the other one. And it's really hard to represent these things on a flat piece of paper. But here we've got these 2 vectors. We're going to add A and B first. We're going to draw the parallelogram. And so the sum of A plus B is R. And now we're going to take R and we're going to add C. And we're going to draw a parallelogram, and R plus C is this R prime. So taking A plus B plus C gets R prime. Here we have 3 vectors. This is reminiscent of the trigonal planar shape, right? But this C is a little bit longer. Is it? No, it isn't. They're all the same. So if we add A plus B, we get R. And if we add R and C, they are equal in length and opposite in direction, and so they add up to 0. This is the sort of thing that happens when you have a molecule that has a trigonal planar shape, and all 3 atoms bonded to that central atom are the same. Any questions about vector addition? This is a table from your textbook, common cases of adding dipole moments to determine whether a molecule is polar. Linear, they're going to go in opposite directions. Bent, you're going to get most likely a net dipole here. If you have trigonal planar and you have identical dipoles, they're going to add up to 0. This will be, let's highlight these things here. Maybe a green highlighter. So this one's going to be nonpolar. The bent one is usually going to be polar. Trigonal planar. If you have identical bonds, that one's going to be nonpolar. Tetrahedral will be nonpolar if you have the same bonds, and trigonal pyramid will be polar. These are only going to cancel out, though, if these bonds are identical. If this is like oxygen and that's fluorine and this is carbon, you're going to have to think a lot more about it. CF4. Determine if CF4 is polar. What do we have to do first? Lewis structure. What's the molecular geometry? Tetrahedron. Polar or nonpolar? Nonpolar. Are we guessing? No, we're not guessing. Carbon-fluorine bond, carbon-fluorine bond, carbon-fluorine bond, carbon-fluorine bond. Those 4 bonds are identical, right? And this spreads out in 3-dimensional space. So that they're all pointing away from each other at equal angles. Those vectors are going to add to 0. Oh, okay. I thought I put the slide in here. I did not. Do you want a faster way? That'll work most of the time. Yeah, most people do. Okay. Molecule is nonpolar if 1, no lone pairs on the central atom. 2, I'll just start over. Oh, forgot something. And both of these things have to be true. Atoms bonded to central atom have the same electronegativities. A molecule is nonpolar. That's such a mess. A molecule is nonpolar if both of these things are true. There are no lone pairs on the central atom, and the atoms bonded to the central atom all have the same electronegativities as each other. So let's do an example. Let's look at this guy. So here we've got carbon and chlorine and chlorine and chlorine and hydrogen. And of course there's lone pairs on these guys. Not that we really care about them, but I'll put them in there anyway. Are there any lone pairs on the central atom? No. Do the atoms bonded to the central atom all have the same electronegativity? No, they don't. Is this polar or nonpolar? This is going to be polar. Why does that trick work? This has no lone pairs. The groups are arranged symmetrically. That's what you need for things to cancel out, for vectors to add up to 0. But this carbon-hydrogen bond has a different electronegativity difference than the carbon-chlorine. And because you have three that are the same and one that's different, they're not going to add up to 0. And it's going to be a polar molecule. How about something like water? Are there lone pairs on the central atom? Yes. We don't have to go any farther. Polar. Has to be polar. Because this makes a bent structure. And even if these two vectors, these two dipole moments are the same, there's no way they can add up to 0. They're going to add up to something like this. So if there's lone pairs on the central atom, it makes that atom lopsided. And this is not going to work every single time, but it's going to work almost all the time. And in my book, that's good enough. I do want you to understand that it's based on adding vectors. Any questions? Let's see, where were we? Molecular shape and polarity. The polarity of molecules has a huge effect on their properties. Polar and nonpolar molecules have very different properties, just like oil and water. Oil is nonpolar, water is polar. They don't mix together, do they? Italian salad dressing, you have the vinegar and the oil, and you can shake it up, and it looks like it's mixed up, but as soon as you stop shaking, it starts to separate. And that's because the interactions between the molecules are completely different. The two water molecules illustrated here are both polar. There's a partial positive on this hydrogen and a partial negative on the oxygen. There's an attraction, an electrical attraction between the opposite charges. It's like the attraction between the opposite poles of the magnet. Polar molecules have this attraction between opposite charges. Nonpolar molecules do not. They don't have partial positive and negative charges. And so what happens is a little bit like if you mix a bunch of magnetic marbles. Here the solid colored marbles are magnetic. They stick to each other. And then we have the regular glass marbles. You can put these in a bag or a bowl and shake them up, and what's going to happen? The magnetic marbles are going to clump together because they have this magnetic attraction. And the glass marbles do not have that attraction, and so essentially they get excluded. It's not that they're having their own little attraction fest over here by themselves. It's that they got excluded from the water. So when you mix up the oil and water and then let it go, the water molecules stick to themselves and they push the liquid oil out. And the reason the oil goes to the top is because it's less dense. There are other nonpolar substances that are more dense than water, and they'll get pushed out and they'll go to the bottom of the water. Any questions? How soap works. Soap is good. If you've ever used Crisco to like grease a pan or something, you know that it's very greasy and it doesn't wash off with just water. Butter doesn't either. It just doesn't come off, or Vaseline or anything really oily like that, or I don't know, engine grease, right? It just doesn't rinse off with water because it's nonpolar and it doesn't interact with the water. You need some soap to get grease and oil to rinse off. The water's polar, the grease is nonpolar. Soap molecules kind of act as a go-between between the nonpolar and the polar. So here's an illustration of a soap molecule. One end of the soap molecule is polar, and the rest of it is nonpolar. We think of this as the nonpolar tail, and this is the polar head. The polar head can interact with the water molecules And the nonpolar tail can interact with the grease molecules. Do I have a picture? No, I don't have a picture. I'll have to draw one. I'll subject you to my horrific drawing once again. And so what these guys do is they make what's called a micelle. Kind of like circling the wagons in the pioneer days. And so the little polar heads will be out in the water where they're comfortably interacting with the water molecules, because these have charges and the water molecules have charges. And the tails will be next to each other. They're being excluded from the water because they're not polar. And the grease that you're trying to wash off will get along just fine in there. And because it's surrounded by all these little polar heads, then you've got this little tiny particle that can wash away. And that's how soap works.